You might have seen insects that are able to walk on the surface of the water, or you might have seen or tried to put a paper clip or a needle on the water. Since these are denser than water, you might expect it to sink, but they're actually floating on the surface. So, why does it happen? Due to the cohesion of the water molecules, free surface of the water behaves like a stretched elastic membrane supporting the particle on the surface. Because of this property of the liquid called surface tension, the particle or material can float on the water surface even if it is denser than the water. Let's imagine that we slice the water surface with a sharp knife. Because of the surface tension, water molecules of each side attract with each other and tends to shrink toward each side. Surface tension can be defined as this attracting force acting per unit length on an imaginary line drawn on the liquid surface, and the force here is called capillary force. Since the surface tension works to minimize the surface area, when we remove the particle on the water surface, it recovers its shape back to the original flat surface, which has the minimal surface area. Any interaction or behavior of particles or things on the fluid interface that is due to the capillary force is called capillary interactions. When a particle denser than water is sitting on the water surface, first, there's a gravity pulling it down, and buoyancy force pushing it up, and finally capillary force along the circular contact line between water and the particle. To predict the particle behavior on the free water surface, let me explain what Bone number is first. Bone number is the ratio of the gravitational effect to the capillary effect. Here, gravity and buoyancy are the gravitational effect, and the capillary force is the capillary effect. Since the directions of the gravity and buoyancy are opposite, we have to subtract one from another to get the total gravitational effect. The difference in these two forces comes from the different density of the particle and the water. The Bone number can be estimated in this final form. Two raw terms mean the density, and g means gravitational acceleration, gamma is surface tension of the water-air surface, and d is the diameter of the particle. Because of the square of the diameter in this equation, we can expect that the Bone number highly depends on the change of the particle size. If the particle is bigger, the Bone number will be larger. As an example, let's calculate the Bone number for an aluminum ball on the water surface. If the particle diameter is 1 cm, the Bone number is 23.3, which means gravitational effect is 23 times larger than capillary effect. What if the particle diameter is 0.5 mm? The Bone number becomes 0.053, that means gravitational effect is much smaller than capillary effect. So, if the particle is large, the system becomes gravitational effect dominant, and if the particle is small, the system is capillary effect dominant. Let's see what does this dominant means and how it affects the behavior of the particles. Let's take a look at the large particle case where the gravitational effect is dominant first. Since in nature, denser material tends to go down and lighter material goes up, light particle on the water surface pushes surface upward and the dense particle presses it down. Capillary force keeps the particle from flying away from the surface or sink down, but the amount of the force is not enough to determine the meniscus shape. Also, this property of denser material to go down and lighter material to go up determines how the particle will react. Before I move on to how actually the particle interacts, let's define the sign convention. If the wall of the water bath is hydrophilic, there will be concave meniscus generated near the wall, and in the hydrophobic case, the convex meniscus will be generated. For the meniscus that is going upward, let's call it as positive capillary charged or positive meniscus. And for the meniscus heading down, let's call it negative capillary charged or negative meniscus. Let's start with the light particles that are deposited on the water bath with hydrophilic wall. Since the light material tends to move upward, the particles are climbing up the meniscus near the wall and climbing up each other. When the bath wall is hydrophobic, the meniscus near the wall will be opposite. Since the particles do not want to go down, in this case they stick to each other but do not cling to the side. The common example of the light particles with hydrophilic wall case is the Chereas effect. In the case of dense particles, they tend to go down, so in the hydrophilic bath, they clump together but are not attracted to the wall. If we change the wall property to hydrophobic, they will still attract each other and also cling to the wall. Let's put every cases together to see if there is a common rule. For light particles in hydrophilic bath, the positive menisci attract each other. In hydrophobic bath, light particles get stuck to each other but repel the wall with negative meniscus. In dense particles in the hydrophilic bath case, the particles also attract each other but move out from the wall that has opposite sign meniscus from the particle. In the last case, every meniscus has the same negative sign and they all attract each other. From the result, we can conclude that if two menisci have same sign, they attract, and if the signs are opposite, they repel each other. Let's compare our prediction with the experiment. The particles are 1.5 cm in diameter, and the blue particles are laser cut out of the acrylic sheet, which is denser than the water. The light yellow particles are made of MDF, which is lighter than the water. These particles are placed on the water surface in the hydrophilic bath. Light particles climb up the meniscus heel on the side wall, and dense particles are attracted to each other, and since they're repulsive from the wall, they stay on the center of the bath. How about particles in the hydrophobic bath? The bath is coated with hydrophobic spray, and you can see that the dense blue particles that form the cluster on the center in the hydrophilic bath now stings to the wall. Let's move on to the small particle case. As we discussed before, if the particle is small, then the gravitational effect is negligibly small compared to the capillary effect. So, the density difference, which is the physical origin of the gravitational effect, cannot be a dominant factor over the interaction between particles. Instead of the density difference, the driving force in this region is the capillary force to minimize the surface area. If there is a particle on the water surface, it distorts the surface and creates the meniscus. This meniscus shape changes the surface area. So, the goal of the capillary force on this region is to change menisci shape or move particles to overlap or far apart each meniscus to obtain the minimal surface. Before minimizing the surface area, we need to know which properties of the particle determines the meniscus shape. There are many factors such as shapes of the objects, wetting of the faces, tilting of the objects, interfacial free energies. All of them influence the shape of the menisci in this region. To make the discussion simpler, let's set every other factor the same for two particles, but the wetting of the faces. Blue color represents the hydrophilic faces, and white color means hydrophobic. For the hydrophilic particle, the side of the particle lacks the water, so the water is attached to the wall and creates positive meniscus. For the hydrophilic case, the side repel the water molecules. It makes negative meniscus around the particle. Let's see how the particles with their own meniscus interact with the others. Since the physical origin of this region is minimizing the surface area to minimize the surface energy, we'll consider how the surface area changed. Let's think about two hydrophilic particles. What if they gather together? The surface area outside the particles remained the same before and after, but the area between particles is disappeared and new surface is created. By comparing the lengths of these disappeared and created length of this 2D model, we can see that the surface area gets smaller when two hydrophilic particles clump together. Similarly, for the hydrophobic particles, when the particles are attracted, the area outside the particle remains the same, and the disappeared surface is larger than the new area created from the movement. So, it means since the gathering of particles with the same wetting property reduces the surface area, the particles will behave in this way. Let's take a look for each case. If hydrophilic particles are dropped in the hydrophilic bath, since the wall and the particles have the same wetting property, they attract each other, and also particles are gathered. In the case of hydrophilic particles in the hydrophobic bath, the wetting property of the wall and the particles are opposite. Particles approaching the wall does not reduce the surface area. The particles only attract with each other, but not the wall. Same things happen in the hydrophobic particles in the hydrophilic bath. With the opposite wetting property, particles and the wall repel, and particles will gather in the center. In the last case, hydrophobic particles in the hydrophobic bath, the particles clump together and also clings to the wall since this behavior is minimizing the surface area. By doing the same analysis we've done for the large particles to find the relationship with the meniscus sign and the interacting behavior, we can conclude that the menisci with the same sign attract, and the menisci with opposite signs repel each other. Although the underlying physics is different for large particles and small particles, in practice, the guiding principles remain similar for those two cases. Let's see the experiment with small particles. The blue particles are hydrophobically coated, and the yellow-brown particles are hydrophilic. The same material, MDF, is used to make both types of the particles to vanish the effect from the density difference. Coated particles are colored with blue marker before the coating to identify which particles are coated and which are not. In the hydrophilic bath, the hydrophilic particles have the same sign with the wall, so they are attractive to the wall, and hydrophobic particles move to the center. When we drop the same particle sets in the hydrophobic bath, the same type particles gather, and the hydrophobic particles are attracted to the wall that has the same sign meniscus with the particles themselves to minimize the surface area.